Let's take a look into how generative AI works. We'll first start by looking into generative text and especially into large language models. So when we look a little bit closer to the more recent history on where generative large language models are coming from, we'll see that there was an event in the mid of the 2010s that inflicted a little bit of a change in the general AI research scape, in the AI practice in industry, and in the types of things that we could do. Because in the 2010s, and especially around that time, 2013, 2014, researchers figured out how to use GPUs, so graphics processing units, to compute large neural networks. The concepts from neural networks have been around actually since the 1950s, but they were until the mid 2010s not really practical because you needed a lot of computing power that usually only supercomputing centers had available. But in this new development where people started to use GPUs to go and train neural networks and execute neural networks, large architectures of neural networks, which we call deep neural networks, finally became practicable. And that started quite a lot of different activities in research, both and in industry. There were many different approaches on starting not only to use deep learning for making predictions, but also to generate stuff. In 2017, we saw the introduction of what we know as the transformer model. And a transformer model basically takes or is trained on an input from a big input source and can then apply an output on something else. The first transformer models that I can remember from back then were style transfers. So you were applications where you uploaded your picture, and this picture, you gave it an instruction and a sample picture, for example, Van Gogh's Starry Night, and you take a picture of you and your family, and in the end you say, okay, recreate this picture, but in the style of Vincent van Gogh for me. In 2018, there was some developments of not a transformer model, but what we call generative adversarial networks, or GANs, to create more quality content. So the first transformer models had this issue that, there were weird artifacts, it looked a little bit strange, was not really what you were 100% expecting. And GANs took a different approach by having basically two types in your model, one generator and one discriminator. The discriminator was trained on images and classifying images. For example, this is how a cat looks like, this is how a dog looks like. And that's what the discriminator does, and the generator was tasked with create me a picture of a dog or of a cat. And based on the feedback the discriminator gives to the generator, the generator learns how to become better at creating certain things that the discriminator and in the end the user would expect. Eventually there was some sort of a discussion of GANs are better, or for and yes, and when and how for which task. But over the times, the transformer model, so the initial transformer model, became the standard way to go and do large language models, and especially what we know here with ChatGPT is, of course, GPT, generative pre-trained transformer. It is a transformer model. The American company OpenAI created a bunch of different transformer models called GPT-1, 2, 3, and now 3.5 and 4, trained on a large set of data. The generative pre-trained transformer in its third iteration came out in 2020, GPT 3.5, which it was the basis of ChatGPT when it initially launched in the end of 2022, and 2023 GPT-4. But we are always in this course, we are talking of course about ChatGPT, about GPT 3.5, GPT-4, everything that comes from OpenAI. But be aware, OpenAI is only one provider of large language models. There's other models, and you see here on the right how there is an evolutionary tree of different large language models, how they were used and how they build up on top of each other. Some of them are open source, some of them are not. This here is a picture from early 2023, so by the time you're watching this, there's probably a huge set of branches that additionally come to that, and not only these couple that you see here. But generally, they are all trained on data sets to reproduce natural language in a way. How that works, and especially with the transformers, we have to talk about maths, we have to talk about modeling tokens, so more or less words as numbers, and predictions. And that's all the generative AI magic, and especially here for generative text, we are taking this now as our first step. So maths, don't be worried, this is not going to be a maths lecture, but I want you to understand very high level what the maths behind it is. So you know from college and from middle school that we have something that we call a mathematical function. A mathematical function here, a function of x is x squared, is taking an input, that you see here on the left side, and is producing an output regarding to a specific rule. Yeah? And in here is square my number, that's the rule on how to bring this output. So if we are drawing here little bubbles, we have basically an input here depicted in green, we have a function, and we have an output depicted here in black. When we think about these type of generative AI models, they are just a very complex function that is adjusted over time. And with very complex, I mean a function that takes many inputs and creates one or more outputs. And with many inputs, I mean potentially millions in the terms of generative AI. And also the output, or the rules, the formula, how we create the output is not as simple anymore. So you see here a picture where we have depicted all the different inputs that are taken as the input to our formula. And this formula, this function that we have here, is very complex. It has different steps where one of these little intermediate steps takes all of the inputs from the previous steps, multiplies them by a certain weight that they have. So each of these edges in here has a weight, and sums them up to create its intermediate results. Then feeds into the next, then feeds into the next, and feeds into the next. By the look of this, you have here basically these little cells that take input, which produce outputs, and are interwoven to each other. It represents a little bit how the things our heads work. And when I tell you that these things in our heads are called neurons, then you know why this thing is called a neural network. And when we have in a neural network many different layers that we put next to each other, we call it a deep neural network. That's where the term comes from. So we say it's a complex function. We understand now what is a complex function, but we need to understand now what means adjusted over time. And that's where training a generative AI model, or generally a neural network, comes from. So think about this example. In the end, you take here an input, and you are taking your input from a large set of data where you know inputs and outputs all together. For example, text, where you know what is the input and what's the next word, but we'll get into that in a second. And you are training your network by basically giving the inputs to your network and looking what the output is going to be. And then you compare the the output of what your deep neural network produced for you with the output that you know that is actually true. And based on the difference between them, you have what we call an error. And there is a set of algorithms that called backpropagation, where you can basically retrain and rebalance the weights in your network to minimize the error, so that the next time you make this calculation, this evaluation of the neural network, the error is smaller. And we do this with a lot of different data points over and over again until our error is as minimal as possible. And that's really the intelligence that comes into artificial intelligence, right? This is statistics that we learn to reproduce certain patterns that we have in data, so that the error is as minimal as possible. It's not that there is some omnipresent person sitting in there. It's not little aliens that make artificial intelligence magic. No, it's just statistics, it's learning, it's training, and getting that back. So we talked about numbers, we talked about functions. How do we talk about words now? Let's take, for example, this set here. So the cool penguins live at the South Pole. This text, we can create this text, or we can stem this text into different what we call tokens. And a token is basically a representation of a word in a number, where the same words have the same numbers. So you see here the cool penguins live at the South Pole sentence. You see D1 cool 2, penguins 3 live 4 at 5, and then because it's the same word like here, again 1, South 6, and Pole 7. That's basically how we represent words as tokens. Sometimes it's a little bit more complicated, so not one word is one token, but generally for a rule of thumb, we take that now. So the last part of that generative AI and large language model magic is the cool penguins live at the South Pole, predicting the last word in the sentence based on the input sentence. And we do that basically by taking these number representations of the things that we know, and we predict the last word in the sentence. And we do that basically, or when we do that, we basically evaluate a neural network. So we got data that we are putting in this neural network, and we take the first 7 words here as an input. We evaluate our neural network. We look what the output is, and we calculate the error to the actual output, because we know the actual output, because we know that the last word in here is pole. Then we take this as our baseline. We see this, it should be here 7. If our neural network calculated something else than 7, then we have to create an error, do backpropagation, and retrain our network. And in this way, we teach a neural network to produce or predict the next word in a sentence based on some previous input. And that is basically all that GPT-3 and GPT-4 are doing, and all of the GPTs are doing. They take inputs, produce outputs. How do we get from predicting words to predictive sentences? Well, the cool penguins live at the, then you predict south, then you take the cool penguins live at the south, and you predict pole. So you iterate over it until you have a whole sentence, a whole paragraph, a whole book, if you want to. And that's all that that this model does. The model is very, very complex, and nobody can really explain how the different things that are connected in there to work. And also OpenAI doesn't really tell you the exact architecture and everything that happens right now in GPT-4. So we take it as a black box. We know on a high level how it works, but now we need to know where it gets its intelligence from, its information from, because these large language models have been trained on a large data set of different inputs. And with large, I mean really billions and billions of tokens that the large language model used to train itself to predict language. And here's a little picture of GPT-3, and that you just have a feeling for the amount of tokens and the amount of words that we're putting into this training of this large language model. They took, for example, articles from Wikipedia with over 3 billion tokens, so 3 billion words more or less, books with over 60 billion words, text, and the largest portion is text crawled from the internet, filtered with over 400 billion tokens. So that's why it's called a large language model, because there's a large amount of data where it was trained on to predict things. And when we talk about prediction, we talk about every time you are working with such a large language model, there is not one answer, but there is a probability of a certain size that a certain word comes next. So whenever we type in the cool penguins live at a large language model has internally a table like this where it says, okay, south has a probability of 0.3, so about a third. North has 0.2 and zoo has 0.19. And what this large language model then does, it basically throws a dice and selects one of these words where the dice throws. But the dice is not correct. It's rigged so that these the words with a higher probability land on the upside more often. So that's where there is a little bit of randomness coming in. That's also the reason why every time you put even the same language, the same sentence, the same prompt into ChatGPT, you will always get something that is slightly different. You can tweak these things and how different they are by going and looking into hyperparameters. Hyperparameters basically modify how this evaluation process is working without doing anything with prompt engineering. So we have in OpenAI here in GPT-3 and GPT-4, for example, the temperature, the temperature hyperparameter. It's a value between 0 and 2 that determines how big the randomness of the sample is. So how far you go and how creative it is what comes out. We have a maximum length hyperparameter where you can determine the maximum length of the output. You have a top P parameter, and that top P parameter basically says how far do you go down this list of probabilities to make a choice. So if you have, say, you only go into the top two things, then every time you put in the penguins live at D, it can only be south or north. Zoo will never come because you define the top P doesn't go down that far. Then you have two additional parameters for frequency penalty and for presence penalty. That helps you to reduce the amount of words or the amount of repetitions of a certain word or the presence of certain words overall. You can tweak these hyperparameters in the OpenAI playground or in the OpenAI API or in EndEngine that I will show you later. Where you can play around and do experiments with, especially with temperature, with top P, and with frequency penalty. So we know now a little bit generally how these large language models work, how neural networks work, but the process for creating an actual chat interface, an actual model that can answer prompts easily is a little bit more complex. And this diagram you see here comes directly from OpenAI, and this was being used to illustrate how the tuning of such a base large language model was happening. So imagine you have trained this model that I've just shown you step by step with over 500 billion tokens from different text sources. You still want to make sure that the answers that you get are very much aligned with the answers that a human would expect according to the quality a human would expect. So what OpenAI was doing having another three-step process next or after the initial training of the model. And what they were doing is basically they created a different set of prompts from a prompt data set. For example, here, explain what reinforcement learning is to a 6-year-old. Then they had real human beings, contractors, who were tasked with, okay, here is this prompt, answer this prompt for me. You have here the internet, here's books, you can Google, you can do things with it. Tell me what the output of this is going to be. And based on this good answer, this really good answer from a human being that was generated, and the answer that the large language model would usually take, they did something that they called supervised fine-tuning. And basically in this supervised fine-tuning step, they were comparing these different parts, or the model was comparing these different parts, and was creating and was learning what a human would expect to make their own predictions better. So with that, they fine-tuned the model. In the second step of their process, they were creating a reward model. A reward model is basically telling how good is which answer. So what they were giving was they were asking their model to create different answers for the same prompt. And then they gave these different answers from the same prompt to a human to rank it according to how good they think a certain answer is. And based on that, again, they retrained their model with this reward model, or they added this reward model to their model in the evaluation, so that every time we are asking something, we can go back to what they created in the third step, a policy. And that policy the policy is basically a representation of the two previous steps and how good the answer is, with giving a certain reward number to it. So every time you are executing something, actually this reward model is leveraged in the end so that you have a good quality output. And that's really the new thing that came there with ChatGPT and with GPT-4, that this was actually qualitative so good that it could help you in real world for many different use cases. But what this means, we now know how generally large language models work, but this means the models are bad at a lot of things, but mostly at 4 things. First off, citing sources. Because of the way that this text is generated, it's not a web search, right? It's not that there's one single source. It's basically all of these 500 billion or 600 billion different tokens that were coming in, and the statistics behind that, the maths that produce then the sentence that you get out when you write a prompt to a large language model. So there's not one source, but there's a lot of different sources. There's now models that say, okay, we can do citations, but what they're mostly doing, they're creating something with a large language model, and then they're doing a web search to find something that is as similar as possible to what they created, and then they say that's the source. But that is not how the large language model works. This is then logic that you put on top. Bias. So in the beginning, when ChatGPT was coming out, there was some hate speech being produced by ChatGPT, and I saw on LinkedIn people thought, oh, has this thing become now conscious and is starting to become some sort of Turing and is producing hate speech. No, because these large language models are trained on data that somebody has written. Some human being has written the text that a large language model can use. And all of us have a certain bias towards something, right? There is nothing as true objectivity. That might become now a little bit more philosophical, but every person has their specific type of view on something. That there is in society a consensus about certain aspects, and in the text that we have here is of course mostly English written text from Western countries. So it has of course the intrinsic biases of the people that wrote it in there. There are different methods that also OpenAI was trying to get rid of what we consider to be hate speech and to reduce the bias, but in the end, nothing is bias-free, and we have to be aware. Hallucinations. LLMs can provide you often completely false information and telling you very confident that that's what the answer to your question is. And that's what we call an hallucination. So we have a sample set on as an input based on which we train this large language model, what it does and where it can go. But if you ask it something that it hasn't seen before, or where the statistic inference is too low, it will just take the next statistical plausible thing and makes it and gives it to you as an answer, and that produces hallucinations. There are ways to get over hallucinations. I always say take a large language model not as a thing that knows everything, but just as a calculator for words. You have to feed all of the informations in that you would like to have to do some processing of text, but don't let it just hallucinate stuff together. And lastly, large language models are bad at symbolic executions like doing maths, because it's a little funny because they are a piece of maths, but they are statistics. And doing maths like 2 plus 2 is 4 is a symbolic execution. They are not trained to do symbolic executions. Right now, there's a lot of people that add new modules in their large language models that know how maths is going. But then there is, on top, there's a router that's basically saying, okay, go for the statistical way of completion or go for the symbolic way of executing rule-based maths that you have. And when we combine these different things, we're not calling it a pure large language model anymore, but we call it a miracle model, spelled M-R-K-L-E, miracle model. That all means that what you put in as an instruction for a large language model determines very, very closely what the output of it is going to be and the quality of the output. And that means the prompt that you write over here is very important. So we can do quite a lot of things with prompt engineering. That's the discipline that we how we call writing the right questions to get the right answers that we actually expect. And this is a very powerful tool. It's not an art. It's a set of skills that you can learn. You can learn how to use context, how to feed data in, and how to use this large language model not as the knowledge base for all, but just as a calculator for words. You can prompt from different roles and perspectives. You can imitate certain styles. There's more advanced techniques like chain of thought, zero-shot versus few-shot prompting, self-consistency, and so on and so forth. It's non-trivial. It's a set of skills, and the skills are called prompt engineering. So, to summarize this session, generative text is basically the combination of math, modeling tokens as numbers, and predictions. LLMs do not know anything. They just predict by the statistics they learned, were trained on, what most likely comes next. They hallucinate, they have biases, they are bad at citing sources, and they're bad at symbolic execution. And the input determines the output. And that's the reason why prompt engineering is so important.